Okay, so thank you very much, everybody, for coming to today's this intelligent and bioinspired mechanics. This is the fifth or sixth seminar series we have been doing so far, and this series is organized by me. I'm right now a assistant professor, gonna become assistant professor in Queen's University, and also organized by a Dr. David River, associate professor in Queen's University in mechanical and material engineering. Today it's my delightful honor to have a Dr. Sam Rudy, my dear friend. We meet every day, not every day, every week, via Zoom, talk about our life and also research, of course. To describe his work on the data-driven method for interpreted systems, identification, and construct a hydrodynamic database. Just a little bit about Dr. Rudy. Sam is a postdoc right now working with Professor Services like Sepsis, at MIT, mechanical engineering department. Before, he obtained a PhD at applied mathematician from University of Washington, while he worked with Dr. Nathan Koontz and Dr. Steve Brenton. And in his undergraduate, he got a physics, and also a mathematics from Washington University in St. Louis. His research has been focused on uncertainty quantification and system identification, and also recently with vortex-induced vibration, where me have learned so many from Sam on his beautiful method. With that all being said, let me give the floor to Sam. So Sam, it's all yours.
Okay, thank you, Dixia. So interesting. Sorry about that. My computer buttons weren't working. So the talk is going to have two parts. The first half is going to be on sparse regression. And this is a problem I worked on a lot in grad school, and that's gotten a lot of recent attention. So I'm going to talk about the work I did on that, which was focused on kind of trying to learn partial differential equations from data. I'm also going to motivate the idea of using sparse regression as opposed to black box methods by showing some results if I use a neural network for forecasting and why it can hide underlying problems. And because it has received a lot of recent interest, I'll try to make an effort to point towards kind of recent works that other people have done that I think do an excellent job on some of the kind of technical aspects of the problem. And then the second half of the talk is going to be on vortex-induced vibrations, which is a problem I've been working with Dixia on. And so what we're seeking to do there is quantify the force exerted on a bluff body from the flow around it in a way that's useful for kind of large ocean structures. So to start off, what I mean by data-driven forecasting is if you give me a time series, then I want to approximate either a velocity field or a discrete map, which allows me to predict future states. And that's obviously an extremely general problem. But recently, a lot of folks have been using neural networks to do this, either simple feed-forward neural networks or LSTM, or there's a whole zoo of methods. What I'm going to talk about is sparse regression, and particularly for partial differential equations. So what that means is I'm going to try to come up with an expression for lowercase f, so the velocity field, which is made of terms that I can interpret, and I'm going to allow that expression to have many terms, but try to impose that most of them are 0. And this is, in essence, a fairly straightforward problem, but there's a lot of technical challenges. And so I'm going to try to highlight recent work, which I think has done a great job on that. So to kind of go over this again, there are a lot of methods. LSTM is probably the most popular if you're learning a discrete map, but there's also a lot of autoregressive methods for doing this, approximations of operators. And then if you're learning the velocity field rather than a discrete map, then common methods are library methods, which is what I'm going to talk about, and neural networks. And the challenge on this second approach is that you have to compute the velocity from position. And that is very non-trivial if you have noise. So I'm going to motivate sparse regression by showing an example of a neural network that at first glance seems to work extremely well. And then I'm going to show that there are issues with it that you might not get even by evaluating it on test data. The neural network I'm going to use as a canonical example is as follows. So I'll have just a neural network interpolation of a velocity, and then I can feed that network back onto itself a few times with prescribed weights here given by K1, K2, and K3. And using this, I can create a Runge-Kutta time stepper where the only interpolation I have is the velocity, but I feed into my network one time step, and then I get out of the network the subsequent time step. And I can do this for whatever order of accuracy I want, whatever time step I want. And this has been around for a while. This is from a 1998 paper, so long before neural networks were popular. So if I do that, and I take the Lorenz 63 system, so the kind of example you see on the cover of a lot of ordinary differential equation textbooks, and I learn that differential equation, where I interpolate the velocity field to the neural network, and then I take some initial condition that lies on the attractor of the Lorenz system, and I integrate forward, and I get an orbit according to the learned differential equation using the neural network for an extremely long time series. Then I can compare that forward orbit to the true system. And since it's a chaotic system, the exact error is somewhat irrelevant, but the statistics are. And what you see on the left column here are the marginal densities in space. And on the right is the autocorrelation function in each of the three variables. And it's about as good as you could expect. And this is actually trained with noisy data as well. So you can see that if you train a neural network to forecast and you look at some standard metric of accuracy, it can be extremely good. But what this hides is the fact that it's actually not learning a very good velocity field. So on this slide, I have two different data sets in the top row. The one on the left is a long time series of length 10,000, and the one on the right is 100 short time series of length 100. And below those are the velocity fields the network learns on the z=25 plane. And they're pretty different. And then on the bottom right is the true velocity field. And both of these learned velocity fields actually do a great job if I look at the statistics of the orbits according to the learned model. And so using that metric, it's a huge success. I took a nonlinear dynamical system, it's a chaotic dynamical system, and I can recreate meaningful statistical metrics of that system with the neural network. But what you see from the velocity field is if I took an initial condition that didn't lie on the attractor, it's highly likely that it would do something very off, because the neural network can replicate nearly exactly the dynamics where it has training data. But as soon as you move away from that training data, all bets are off. And to give it another simple example, here is just a linear system. So on the bottom row here, I'm showing the training data, which is blue, but this is from a paper where we actually denoised it. So you can view the black spiral as training data. And on the top is the learned velocity field. And this is just a linear damped system. It should look like the top left, but obviously as I use nonlinear models, so if I add layers to the network, then you can see the error increase away from the training data. So that motivates sparse regression. And the idea here is if I have a dynamical model that I can look at and interpret, then for one, a lot of the true models for systems lie in a space that we can guess sometimes. And I also don't have any kind of hidden problems because I understand completely what's going on. So a very, very simple kind of schematic for this is if I collect a data set, say the Lorenz system, then I represent each of the time derivatives variables as a sum over very simple kind of elementary functions, which are given by theta1, theta2, up to theta d for some large library. So these could be 1, xyz, x squared, x cubed, stuff like that. And then I have a regression problem for the weights of each one of those library functions. And I want most of those weights to be 0. So this is kind of a regularization constraint. I'm assuming that I'm giving it many, many more library functions than it actually needs. So I minimize the squared error plus lambda, and this notation, I'll call it the 0 norm, even though it's not a norm, it's just the number of non-zero coefficients. And if I can solve that, then I should recover the governing equations. So to motivate this from kind of a somewhat more rigorous perspective, if I have measurements and of x, and let's call the derivative of xy, then I'm assuming y is normally distributed with mean given by the sum of some number of library terms times their weights. And in some sense, I can formulate this by saying there's a prior on those weights exponentially decreasing in the 0 norm. Then I get this exact problem. And in practice, this capital C here is really just there so that the prior can be integrable. One thing is I will almost never be able to measure the velocity of something. I can measure the position, and then I compute the velocity. And if there's any error in the position, that error is greatly amplified when I take a derivative. So I'll talk a bit about that. And then, of course, this problem is non-convex. It's actually NP hard, so there's approximations that need to be made. In the context of PDEs, so this is work I did in grad school, you can do the same thing. If I have the time derivative of a field, I can set that equal to some sum of simple functions, say u, or the second derivative of u, or the product of those, and take a weighted sum of those functions. And then I have a linear system that looks like what you see on the bottom of the page. I have the time derivative at each position and time step, and each one of those is equal to some sum over library terms times weights. And if I can solve for those weights, then I would get a PDE. So similar assumptions to before, somewhat contrived, but essentially how I get that problem I just showed is if I assume I have normally distributed error from my library to the actual time derivative, and I have this strange prior on the weights, then I get a sparse regression problem. And if I can approximate this, then I will recover the PDE from data. So that problem is very difficult. The most common way of approximating an L0 regularized regression is to change the 0 to a 1, and then you actually have a norm, and it's convex, and it's very easy to solve. And that is in some sense equivalent to what's called compressive sensing. Other methods are greedy methods. The one I used in my work was somewhat of a heuristic method based on sequential thresholding. There's been more recent work in using empirical Bayes, so you get uncertainty estimates. And then there's some really interesting work using information theory as part of a greedy method, which is perhaps the best way of solving this problem. So the way I do it in my past work is just use a ridge regression. The ridge penalty is because the matrix theta is often very poorly conditioned, and then throw out small coefficients and repeat. So at each iteration of this, I'm essentially solving a regularized least squares problem, and then finding a sparse solution close to that, and then recursively applying this to remove library terms. And in summary, kind of the idea is if I have a data set here, showing the Navier-Stokes equations, then I should be able to recover that by taking derivatives of that data set and solving a regression problem. And in this case, I can. And in a lot of other cases, I can as well. On this slide, the data point I want to highlight is the error on the Kuramoto-Sivashinsky equation. If I try to learn this equation here from data and I give it any noise at all, I get 52% error on the learned parameters. And that highlights one of the difficulties with this is that, and everything I've shown so far, I assume I have a big pile of data and that data is not that noisy. I need a lot of data because I need to evaluate derivatives. And to do that, the data needs to be spaced relatively close. And then if that data is noisy, then that noise is amplified when I take derivatives. More precisely, if I have Gaussian noise on some data set and I use finite differences to get the dth derivative, then the error on that derivative I compute is going to grow like delta x, so the grid spacing to the negative d. So actually, as I refine the grid, if you measure data closer and closer, but you have the same noise, your derivative estimates are going to get worse. And this is a big problem, so you can't really use finite differences. Other kind of approaches are you could use a smoothing kernel, so convolve the data with a Gaussian or something like that. That removes noise, but it adds bias. And so if you have a problem with a high order derivative, that bias could cause a lot of issues. You could interpolate locally using polynomials or splines, and that also removes noise and also adds bias. Variational methods, so if you learn the derivative such that the integral of that derivative matches your data, same problem. And you can try to remove the noise using the learned dynamical model. And that works quite well, but it's difficult, it's slow. So more recent approaches to this problem have not used numerical differentiation. So two different ways of getting around this are automatic differentiation. So if I have a data set and I just interpolate that using something that is differentiable, then instead of trying to differentiate the data numerically, I can just differentiate the interpolation. And if I use a neural network or a Gaussian process, that's pretty trivial and works extremely well. The perhaps best example of this is physics-informed neural networks, which use this. And then another way is to just not differentiate the data at all. And so two recent papers have used, instead of forming a regression problem with derivatives of the data, they integrate against test functions and essentially integrate by parts to differentiate the test functions rather than the data. That works extremely well. And just to highlight one of the challenges associated with numerical differentiation. So here's the same problem I showed earlier. This is a solution to the Kermode-Sierpinski equation. This is an equation with a fourth order derivative. And so if I gave you the data set in the top left, which is the true data, and let's assume somehow you had very finely detailed measurements of that with some small amount of noise, then if you take a standard neural network and interpolate that data, then for a large enough neural network and enough training data, you'll do an excellent job. So the bottom left figure here is the neural network interpolation of the top left figure. And you probably can't see any difference because it does quite a good job. And then if I differentiate the true data in time or in space or 3 times in space, then you get the next figures in the top row. And if I differentiate the neural network interpolation using automatic differentiation, you get the bottom right 3 figures. And again, they look almost identical to the top row. But if I take the data in the bottom row and I do a regression to find the time derivative, completely ignoring sparsity, if I only give it the 3 terms that should be there, UUX, the second derivative, and the fourth derivative, then I get about 50% error in the coefficients, even though the neural network auto differentiation looks perfect. It clearly isn't. And the reason for that is the neural network, while it looks quite good, if you take the Fourier transform of the auto differentiated neural network, you'll see that there's a lot of high frequency artifacts. So the neural network might not be smooth. It might learn noise. And this is really hard to see in the space domain. But if you look at the frequency domain, you'll see that the 2 rows don't really look anything alike. Or they look similar, but the noise in the high frequency domain is amplified quite a bit. for the higher order derivatives, and that causes a lot of problems. So that's one challenge. I think physics-informed neural networks get around this by imposing that the neural network actually obeys an equation. But for standard kind of global interpolation methods, it's quite tricky. Another kind of technical problem that comes up here is that I have a linear system I'm trying to invert, and I have this sparsity penalty. And getting a sparse solution to a linear system is a lot more challenging if that linear system has a high condition number. And that is the case for a lot of PDEs. So to give an example, if I think about just a simple 2-soliton solution to the KdV equation, and I have very detailed data of this, and I try to recover a PDE that explains the dynamics, then I get the KdV equation. It's not that hard. But the same equation can give me a single traveling wave solution. And that traveling wave moves at a fixed velocity in one direction. And that's also explained by the advection equation. So if I have a library of terms that includes both the advection equation and the KdV equation, then if my derivatives are perfect, it's actually not even full rank. Here I'm using finite differences to compute derivatives. So I end up with something that is technically full rank, but the condition number is 10 to the 9th. And that's a huge problem. And then if I give it 2 distinct solitons, the condition number drops a lot. But this middle case highlights that if I assume some library fits the dynamics I'm trying to explain, then that library, in many of the examples I've shown, is horribly conditioned. And so this is a big challenge that a lot of these methods face. Lastly, I'll mention that the assumption that PDE fits nicely in a library is often not true. If it has parametric dependencies, then that can be accounted for explicitly in the library. What we end up with is a group sparsity problem where each point in time or in space is a distinct linear system, but they all have the same sparsity. And there are pretty common methods for solving this. There's the group lasso, which is a convex problem, or you can do sequential thresholding methods. And to give an example of that, if I take just an artificial example of a fluid flow, and I just change the Reynolds number halfway through the simulation, then the algorithm can figure that out. And lastly, I'll show the similar example for the Kermode-Sierpinski equation. This is kind of the canonical problem case for this sort of algorithm. If I let the spatial parameters for each term in the PDE vary a little bit, then with no noise, I learn them perfectly. And if I add noise, you'll see on the bottom right here, I've added 0.01%. So that means the root mean square value of the noise is 1/10,000th that of the data. And the coefficients are quite bad. And any more noise than that, and it actually learns the incorrect sparsity. So this again highlights the challenge of this noise. So I guess in summary for the first half of my talk, I think neural networks work extremely well on a wide variety of problems, but they don't always work. And that motivates these interpretable methods. And interpretable methods have their own problems, namely they're difficult to find. They are made more challenging by the presence of noise. They're made more challenging by the presence of data sparsity. And they're made extremely challenging by the fact that you're trying to solve an NP-hard problem by using various kind of convex regularization or relaxations or heuristic methods. And these are all hard, but there's been a lot of progress. And so I hope some of the pointers here are interesting. The second half of the talk, I am going to discuss work I've been doing with Dixia on vortex-induced vibrations. So to start, I'm not sure everyone here is familiar with vortex-induced vibrations. The easiest way to think about them is if you've ever been in a swimming pool and you hold your arm out and move it across your body as fast as you can, you're likely to feel an oscillatory force in your arm. or if you hold it out the window of a car as you're driving. And what causes that is you have a bluff body, your arm, or in this case, we're studying cylinders, and it's moving through a fluid. And as the fluid passes the body, you have vortex shedding, and that causes a periodic kind of asymmetry in the flow. And that exerts a force on the body itself. And so if that body is free to move, then the vortex shedding coming off of it will induce motion, and that motion is periodic. So what we're interested in is kind of the effect of vortex-induced vibrations on large ocean engineering structures. So this could be a cable or a tube, and these are flexible cylinders in a flow. Turns out that's really hard to model, and I'll get to some kind of more specifics of exactly why that is later. But the starting point we take for this is a rigid cylinder. So what we're doing is trying to understand the forcing on a cylinder in a flow, starting from the forcing on a rigid cylinder, and then moving up in complexity to a flexible cylinder. So the starting point for all of this is on the left here, I stole this figure from Dixia. We can, for a prescribed motion of a cylinder, measure forces. And that's the starting point for the understanding of everything that follows. We take a cylinder, or Dixia takes a cylinder, I didn't do this, and pulls it through a tank of water at a prescribed amplitude and frequency of oscillation. And you can measure the forces, and then you can construct databases of the forces on a cylinder due to vortex-induced vibrations. And we take those databases with a little bit of theory, and then we can look at larger experiments or experiments where the motion isn't prescribed in advance, and use machine learning or just optimization to find optimal parameters for those databases. And then after that, we can try to scale towards kind of higher large scale models. Using the databases we've kind of informed by tow tank experiments, and then learned on slightly more complicated experiments. So to begin, the equations of motion for a cylinder moving through water, if I constrain the motion of the cylinder to be perpendicular to the flow of the fluid. So let's say I have a cylinder, there's a fluid velocity past it in the x direction, and the cylinder is allowed to move in the y direction. Then I have the second order ODE, where on the left-hand side, there's the kind of canonical example of a damped oscillation. And on the right-hand side, I have F sub L, which is the force applied on the cylinder from the vortex-induced, or sorry, from the fluid, the vortices. And if I assume that this motion is periodic, so y of t equals the real component of some amplitude times e to the I omega t, then I can decompose the periodic component of the forcing into two terms. The first term is Cm rho sub f v, where v is the displacement volume and rho sub f is the fluid density. And C sub m is something I don't know. So this is an amplitude term that tells me the amplitude of the force in line with the velocity. And the second term, which has an I in front of it, so it's in line with the acceleration, is given by some term CLV, which is the lift force exerted by the fluid. Now, if I take this kind of ansatz and plug it back into the ordinary differential equation, I get a set of two algebraic constraints that tell me the relation between the non-dimensionalized frequency and amplitude, and how those relate to the added mass, C sub m, and the lift force, CLV, where the non-dimensional frequency is given by this expression here, and the amplitude, non-dimensional amplitude, is just the amplitude divided by the diameter of the cylinder. So using the tow tank, we can measure these and then try to get optimal parameterizations of those two coefficients. And once we know those coefficients, we'll know what the response is of a cylinder in a prescribed current. So again, this all starts from Dixia's work on forced vibrations. And what you're seeing here is a picture of a tank that will take a cylinder and drag it along the length of the tank and make it oscillate in a direction perpendicular to the length of the tank at a prescribed frequency and amplitude. And using that, we can say, we can measure forces. You can measure the lift force and you can get the added mass. And then for any amplitude ratio and non-dimensional frequency, you can get a value for those two forces. And what Dixia did is then interpolate with a Gaussian process and use intelligent sampling to get very rapid convergence, so that at the Reynolds numbers that are testable in this tank, we have extremely high fidelity data for the forcing parameters. And that looks like the following. So the top row here is the lift force, and the bottom row is the added mass. And the kind of X and Y axes here are the reduced frequency and amplitude. These values also depend on some other properties of the experiment. So cylinder roughness affects them, Reynolds number affects them, but we're going to focus just on reduced frequency and amplitude ratio and try to reconstruct these databases, first from the tow tank data, and then we're going to try to do it from free vibration data, which I'll explain in a few slides. So this is the parameterization we're using. This we got from Michael Trantafilou, who's a professor here at MIT, and it's been used for a while as a model for these coefficients. And we just made one slight adjustment, which is that this parameterization shows piecewise linear representation of the added mass here on the left, and piecewise linear representations for the lift force at 0 amplitude, and then for a critical amplitude at which the lift force switches from increasing in amplitude to decreasing in amplitude. So what we're trying to capture with this parameterization is essentially the 0 contour, so the red line of the lift force. And since we generally only observe the left one of the 0 contours in free vibrations, that's really what we're going to focus on. And the added mass, you'll notice in the parameterization, is univariate. It is only a function of the reduced frequency, whereas clearly in the database, it's not. It changes with amplitude. So what we're aiming to do is capture the added mass at some horizontal line through this data. And in that case, it does look quite similar to what you see in the parameterization. We also learn a transition length scale between the linear segments. So here, there's a sharp transition. What we do is allow it to smoothly transition from one linear segment to another over a prescribed length scale, which is an extra parameter. So there's actually 14-dimensional parameterization in this case. So to validate this, we have all this extremely high fidelity data from the tow tank, and we can pick a few points and see, just minimize the two norm error between the measured values of added mass and lift and those predicted for that particular frequency and amplitude given the parameterization. So doing that and just picking 4 points, we get the following. So these 4 points shown as the blue dots, we just selected by hand such that the lift is slightly greater than 1, because that's what you would observe in a freely oscillating cylinder. And then taking those and minimizing the difference for both CLV and lift, CLV and CM. The bottom row shows the values we get for each of the 3 Reynolds numbers here, 3,000, 9,000, 12,000. And it's obviously not a perfect match, but there are some key characteristics that we do capture. We get essentially the right frequencies for the 0 contour. And we also notice that the height of the 0 contour increases in Reynolds number. And the height of that 0 contour, so the maximum value on that red line in the bottom row or the top row, tells you the maximum amplitude that you would see in a freely oscillating cylinder. The CM, here top row, we have 3 different cases, 3 different Reynolds numbers of the high fidelity data from the toe tank. And the bottom row, what I'm showing is the parametrized values in red, and then the averaged value over the amplitude ratio of the toe tank data in blue. And for low Reynolds numbers, it's a bit off. That's likely due to this zero contour curving over. And then for high Reynolds numbers, it's actually extremely accurate just from 4 data points. Okay, so the parameterization works with the toe tank data where we have excellent high fidelity observations of the forcing, but a lot of experiments done for vortex induced vibrations don't have measurements of the force. So what we do have is the fluid velocity, and then we have an amplitude and frequency. So essentially I have a nominal reduced frequency, which is related to the fluid velocity. I have an amplitude ratio, and I have an actual frequency of oscillation. And from this, we would like to back out optimal parameters for the added mass and lift. And the way we do that is from those equations of motion, we had 2 algebraic constraints. And these, the first one relates the observed frequency, the observed reduced frequency, to the nominal reduced frequency, which is the reduced frequency we would see in still water. And that ratio is given by the square root of the mass ratio, m star. That's just the ratio of the densities between water and the cylinder. And then the bottom row, we have an added mass term. So using that and the observed frequency and nominal frequency, we can try to determine added mass. The second equation gives us the amplitude in terms of the lift force and a few other terms that we can determine from the first equation. And there's some zeta here is a damping ratio, which we assume we know. So if I have a single data point and I have a parameterization of the added mass and the lift force, then I can minimize the residual error on both of the 2 equations you see in the middle here. And we could weight that by some lambda. And then I would get estimates for the response frequency and the response amplitude that allowed for these 2 equations to hold. Turns out that lambda doesn't matter at all, and I'll show why on this next slide. So, again, if I have a nominal frequency, an amplitude, and a frequency, then if I minimize the residual error on the frequency equation, that'll give me an estimate for the frequency for some given nominal frequency and parameterization. And then given that frequency, I can always uniquely solve the second equation. So it's really just an optimization problem in one parameter for the inner loop. So then if I have n observations and each one has its own frequency, nominal frequency, and amplitude, I can write down a cost function for how well the parameters bold p. So that's the 14-dimensional parameter space that tells us what added mass and lift are, and just minimize the error between what I observe and what I would expect according to the 2 algebraic constraints. And the added constraints here on the right is just, we constrain the values of bold p to be in plausible regions based on what we've observed in the forced vibration data. So this is a bit of a tricky optimization problem. It's non-convex. It's not necessarily differentiable. I don't have access to derivatives where or if it is differentiable. And most routines that are built into computer programming languages fail. So every single gradient-based method I tried failed. Bayesian optimization fails. Particle swarm methods fail. And the way we get around that is more or less by brute force. So we have a coordinate descent method where we randomly sample along each coordinate, select the point with minimal error, and then pick a new direction to sample in. And then after applying that for some number of iterations, we use a line search where there's kind of a more fine tuning And there we do use local gradient information computed with finite differences. So it's a sequence of those two, and then many, many optimizer restarts, as is common for non-convex problems like Gaussian processes. So doing that, I'll show a few different data sets we apply this to. The first is a data set collected by Smogeli at MIT in 2003. This is at Reynolds number 19,000. And this is a very special data set because it is technically a forced vibration data set, but there's feedback control such that the amplitude and frequency matches that of free vibration measurements. So what we have is a data set we can treat as free vibrations to test our algorithm, but then we also have measured values of added mass and lift to compare to at the end of it all. So here's the result we get. On the top row, you'll see the reduced frequency, and the bottom row is the amplitude ratio for different Vn, which is 1 over FRN. Again, that's related to the fluid velocity and the stiffness of the spring we're using. And the experimental data is shown in blue, and the model data is in red, and we get great results. It tracks everything we would expect it to track. And then we also have, from that experiment, we can get, the values for CM and CLV everywhere, not just where we have data according to the parameterization that we're using. So what we have on the left is the lift force, and on the right is the added mass, just as a function of frequency. And here I'm showing the experimental data in blue and the model predicted data points in green. But this data set, we also have measured values of CM and CLV. And CM here, it's actually not, we're not using the measured value of CM, we're using the measured values of frequency and nominal frequency to compute CM. But this, as opposed to 2 slides earlier, again, we see very good agreement. The bottom row is off by, it looks like, some constant multiplicative factor, which could perhaps be explained by our damping ratio being off. But I want to highlight here that the optimization algorithm we used did not see any of this data. So it's recreating the correct added mass and almost recreating the correct lift values, despite not having access to them during the optimization. So we were really happy with this result. The next data set is another data set collected at MIT by Jason Dahl, who I believe is in the audience. And this data set is a little bit more interesting. Well, it's different in that here I have a cylinder in a flow, and the motion of the cylinder is no longer constrained to only be in the perpendicular direction. So now I have cross-flow motion, which is perpendicular to the flow, but there's also inline motion. And what's important to highlight here is this figure on the right. The solid dots show the amplitude ratio in the cross-flow direction. And what you might notice is that in previous data sets, there was 1 peak, and here there's 2. So the previous parameterization isn't going to work very well. And if I apply the previous parameterization and look at the results, I indeed get something that doesn't look very good. The frequency matches, and the amplitude ratio somewhat follows the same trend, but it clearly misses the double peak that you see in the blue dots. So we adjusted the parameterization a little bit. So the frequency is the same. The added mass is the same. The frequency values used for the added mass are no longer correlated with the lift values in the same way. And the lift coefficient is allowed to have 2 peaks. So for the lift coefficient at 0 amplitude and the critical amplitude at which the slope of the lift coefficient goes from positive to negative, those are both allowed to be double peaks. The only thing we impose is that the middle here is lower than both of the peaks. And then we treat this in the exact same way. This is now a 19-dimensional parameterization. There's 18 shown on the figure here, and there's a 19th that we learn that indicates the length scale on which the transitions between linear segments occurs. And when we apply that, we get much better results. So, the Frequency still looks good, and the amplitude now closely tracks the results in the experiment where we have two distinct peaks. The values for lift and added mass that we get when we solve the optimization problem are shown. Added mass clearly hit the boundary of where the parameters were allowed to be. Perhaps that's because we don't have any data for frequencies greater than 0.25. So we were quite happy with this as well. So the last thing I'll talk about is the kind of moving from rigid to flexible cylinders. And this is actually a much more complicated problem, but there has been past work in trying to learn databases here. So we are kind of slowly trying to build on that. So flexible cylinders, just to go back to this summary figure, are a bit harder. Well, they're a lot harder for many reasons. The first is if you want to do an experiment on a flexible cylinder, it's more complicated. You no longer have an amplitude that's constant. It varies along the length of the cylinder, as does frequency. And if you want to do computational fluid dynamics for a flexible cylinder, you can do that for a small flexible cylinder, but at the scale that folks are interested in for kind of large ocean engineering structures, you're looking at Reynolds number 10 to the 5th and a length to diameter ratio of 10 to the 4th. And that is completely intractable for CFD. So the way people approach this problem is to develop models for rigid cylinders and then treat the flexible cylinder as a chain of rigid cylinders that are coupled together, of course, by the stiffness of the long flexible cylinder, and to use a PDE to model it. So that PDE is given by the top row here. So it is somewhat similar to the ODE we had for the rigid cylinder case, and we're going to use a similar approach where we're going to decompose the solution into modes y of z, and each of those is going to oscillate at some frequency e to the I omega t. And then we can decompose the periodic component of the forcing as before. There is an added mass portion, which is in line with the velocity or in phase with the velocity, and there's a lift portion, which is in phase with the acceleration. Now, plugging this ansatz into the PDE, you get an ordinary differential equation. And this is what we solve to get modes and frequencies. Interestingly, that if you integrate against the complex conjugate of y, you get a nice interpretation of this as two different integral equations. One relates potential and kinetic energy, and one relates dissipation to the power put in by the lift force. But what we're going to use is the top equation, the nonlinear eigenvalue problem. And this we can use with a semi-empirical code to determine y, so the mode and frequency. And here I'm plotting the resulting mode for one solution of that. This is called a semi-empirical solver, the code we use to do this, because we have the PDE, but the ODE also has CM and CLV. And so to solve that ordinary differential equation, we need kind of functional representations of those two coefficients. And those are, of course, empirical. So this is the output of a code called VIVA, vortex induced vibration analysis, which was written here at MIT. And what we can do is take experiments of which we have a moderate number of flexible cylinder experiments of length 38 meters in prescribed flow profiles. So this top figure, what you see is the x component of the flow as a function of z. So this is length along the cylinder. This is a shear flow where it goes from 0 to 1.5 over the 38 meter length of the cylinder. And then the surface figure here is the response. So that's the amplitude of oscillation. And you can see it's pretty predictable behavior. You have a mix of traveling waves and periodic motion. And then if you Fourier transform that data, you get a very distinct peak around f equals 6 and another around f equals 17 or so. So previous approaches to this have taken a parametric database and tried to minimize the error to some particular experiment. So that was done by Harish Mukundan. It's written up in his 2008 PhD thesis at MIT. And what he did is take this cost function here for a single experiment, so n equals 1, and minimize the mean square error between the mode output from VIVA, the semi-empirical code, and the time average of the experiment. And then there was also a penalty on the frequency. So what we're doing is taking that with a slightly updated parameterization for the database, which was informed by the experiments of Jason Dahl, and essentially faster computers, and using it on a much larger data set. So for n equals 1, I get the following result. If the black dashed line is the original parameterization used in VIVA, and the blue is the experimental data, then what I get as a result of the optimization is the red, and you can see the frequencies also match almost exactly after using the optimization, whereas beforehand the frequency was off by 50%. And here are the databases we learned. That's n equals 1. If n equals 16, then this is showing the training data. The black dashed line is the kind of nominal database that we started with. The blue is the exact training data, and the red dashed line is the optimized values. And you can see both the normalized root mean square error and normalized mean average error for frequency are significantly lower after optimization. That's on the training data. And then testing data, we get a similar result. The root mean square error for the optimal parameters increases slightly from the training data, but not much. Likewise, the frequency error increases slightly, but well, it increases about 50%, but it stays low. And both of them show a significant improvement over a database optimized for one example. So with that, thank you very much for your attention, and I'd be happy to take any questions.
Okay, thank you very much, Sam, for this long talks and a very informative talks. So let's open the floor first to the audience. If there's any questions, please raise your voice and just directly raise ask your questions.
Sam, can I ask a question about the first part?
Yeah, absolutely.
Sorry, I realize that the last part is probably more exciting to you because it's your latest work, but I really was amazed by what all the things you said in the first part, and honestly, I'm not so familiar with it.
Okay.
So, for instance, I work a lot with NLS and higher order NLS, and then if I want to see what one term does in the equation, I have to do the whole simulation again without that term, and then see what changes. So how can you, when you say you build a library of all possible terms and then some show up, how do you practically do that? How do you build that library?
So I think it's quite a bit easier than what you're doing. Basically, I assume I have some solution to the PDE. So if you solve the NLS equation, say for some initial condition in time, then I take that full solution, and one of my library terms is the solution itself. One of the library terms is the x derivative. One of them is the second x derivative. For NLS, if your data is complex, you could look at the absolute value. I guess you have to for NLS. So basically, it's just looking at a single data set and looking at different kind of transformations of it, and each one is
okay. But I mean, if you have a solution field, the x derivative is going to be different at each point in that two-dimensional field in space and time.
Yeah. So each library term is a vector of size your data set. So if you have an m times up simulation with n grid points, then each library term is an n times m vector.
I see. Okay. Oh, thanks. Thanks a lot for clearing it up.
Thanks, Debbie. Any other questions? Okay, if not, like, I want to say thank you. Like, let's give virtual thank you to Sam. Like, I will just like, showcase as representative all other people like clapping their hand. So thank you very much, Sam. So like for your talk. And as like I mentioned, this video will be like posted later, like, in the YouTube and like, in the like, Chinese website. At the same time, so I also want to say, like, since next week is APS and Thanksgiving. So first of all, happy Thanksgiving for everybody. So like, and also our talk like series will be stopped for 2 weeks, giving like, giving room to APS DFD, division of the fluid dynamics, and we'll resume in 2 weeks. So with that, thank you very much for your attention, and like, I'll see you guys in 2 weeks. Bye-bye. Thanks, Sam.
Yeah, thank you, Dishan.